All right, I'm going to go ahead and get started with our announcements. Welcome everybody to our June CBEC meeting. As you probably know, CBEC is a nonprofit organization that is designed to help further technical knowledge and building construction throughout the greater Northwest. We have a number of ways of doing that, from these educational meetings to scholarships for students and our research grant, which I will talk more about in a moment. My name is Nathan Sini. I'm an architect with Morrison Hershfield here in Seattle. We have a great board that supports all that we do. Amelia Davis is our secretary, Jeff Didion, our treasurer. Sharon Libby is our education chair, who is on maternity leave. And Amanda Pratt is our acting education chair. Cliff Marvin is in charge of membership. Hillary Roy does our venue coordination, which will become more important this fall. Joel Thornburg is in charge of sponsorship. If you're interested in sponsoring a future CBEC meeting, reach out to Joel. Bill Thordarson does our student outreach. Grace Wong is in charge of communications. Jeremy DeWitt manages our website. Penny Short is our board administrator. And we also have Phil Martinson, who is our Spokane representative. We are merging with the Spokane BEC to kind of broaden CBEC's reach and try and engage more with Eastern Washington, as well as the surrounding areas out there. So as we continue to do virtual meetings, we will try and engage more with folks on the east side and to get some appropriate education out there. I lost my button. There it is. Another piece of this is that every June we elect our board. What we have is a slate of board members that the current board has selected. So these are, folks that I just listed as the current board members, with the addition of Phil to be a Spokane representative. I would like to get, I was going to try and figure out a poll, but now I'm not sure how to do that. I don't know, that's not working. Anyway, if I could get those of you present to put a, how about you message me with a yay or a nay, and then we can get the approval of the membership to proceed with the board. As always, if you're interested in joining the board, please reach out to myself or another board member. We're always happy to have more help and support to keep building this organization. We have just launched our second annual CBEC research grant, which is a grant of $2,000 to promote building knowledge and science in the Northwest. If you're interested in doing research or crowd development, that wasn't the right words. If you're interested in doing research, whether it's a hands-on project, whether you're developing software tools like our previous research grant, grantee is doing, you can find the application information and the grant information at cbec.org/opportunities, and those are due in on 10/29. So you have a bit of time to put something together, but we're looking forward to seeing what you guys come up with and reviewing applications. A couple other events around the area. CSI Puget Sound has a chapter meeting on September 9th. And their national conference is 9/22 through 24. IBEC Puget Sound, the Region 5 virtual meeting, which is sort of the western half of the country, is from 6/22 to 6/24. And locally, their annual Doug Jason golf tournament is coming up on 9/10. I've mentioned before the Wagdy Anna Symposium, which is being put on by the Boston BEC. And September 23rd. Keep an eye out for that. It looks to be a good event again. Now I'd like to bring in Frank Calabrese, who is a rep with CECA, who is our sponsor for today's meeting. Frank, thank you very much, and take it away.
Okay, thanks. Let's hope this works as well as it did in practice. Fantastic. And I'm going to start my clock because 5 minutes, I promised I'd do it in 5. And those of you who know me know that'll be a challenge. But good afternoon, everybody. I'm Frank Calabrese with CECA. And in my 5 minutes, I want to introduce a brief introduction of CECA. We're going to talk about all the different divisions and how to find the correct local rep. Introduce you to our Pacific Northwest reps for my district. I want to highlight quickly 4 products and then talk about CECA Knowledge Center and some continuing education credits. So what do you know about CECA? Most people say our sealants, some people say our repair mortars. But actually, I'm going to go through this very fast. These are just the companies we have in our construction division. RSB is the division I work for. And RSB is the commercial refurbishment, sealing, and bonding division. We have your structural straightening FRP products, your deck coatings, your sealants, your repair mortars, your modified mortars, polymer modified, and products of that nature. So locally here in my district, it's Oregon, Washington, Idaho, and Alaska. And I have Serge Alexander living in Portland, and you can see his information on the board. He takes care of Oregon and Idaho. In Washington and Alaska, we have Jeff Del Plane and Steve Nagabani. Steve is our newest member. He's been with us about a year, a little over a year, and I'm running around trying to make heads or tails of what everybody's doing. So let's talk a little bit about CECA before we jump into all the products. The 4 new products I want to highlight, but if you don't know CECA, we are over 100 years old. We operate in over 100 countries. The RSB division, my division, one of the nice things is where CECA operates in a country, they try to manufacture in that country. And 99.5 at least % of the products that we sell in commercial RSB in the United States are manufactured in Southern California, Northern California, Texas, Ohio, and New Jersey. CECA is an $8 billion company plus, and we have over 26,000 employees worldwide. So many folks call me and say, you're CECA, I want Sonofill roofing, which is fine. If you are not sure who your rep is or what division they belong to, feel free to call any one of us and we'll be happy to direct you to the right person if we can't ourselves. So let's highlight 4 new products. Most of you are familiar with deck coating products and the textured deck coating products. From that technology, we have come up with One Shot. So we still have our single component urethane deck coating systems for pedestrian, single component for vehicular, multi-component for pedestrian or vehicular, and our hybrid systems. The hybrid systems would have your urethane base, an epoxy intermediate coat, and then urethane or 2 urethane top coats. What we did is we took that technology, and when you do the multi-systems, you have to make sure you prime, and then the base coat, and then the intermediate coat, the top coats, and they all have wait times in between. With this new one-shot technology, everything is mixed in one pail, then it's spread out with a squeegee, back rolled north, south, east, west. You walk away, it's done. You have your base, your top coat, your wear surface, everything. The 721 shot is for vehicular traffic. The 726 balcony is for pedestrian. The 726 balcony you can actually walk on within 8 hours. So 7600, that is our 2-component polyurethane bitumen modified waterproofing membrane. This is great for tank liners, pond liners, cooling towers. Our 360 SCC, this is our self-consolidating concrete mix. Now, a lot of you know or probably know our Secret 211 SCC. fabulous product. We still sell it, make it. The 360 is new to this year. And the 360 is great because in one lift, you can go to 24 inches, which is pretty amazing. So again, here are our reps in the Pacific Northwest. And if you are interested in continuing education credits or just finding out more about CECA, there's two avenues. You can call us, and now CECA has opened us up, especially those of us who've been vaccinated, to come out and do box lunches, or we can do presentations over MS Teams, and you will get continuing education credits and or AIA credits if you have an architect there with an AIA number. One of the new things, if you can contact us, we can get you a link to the CECA Knowledge Center. And that's where you register, you go in on your own, there's icons for all the different divisions, and you can do these 1-hour sessions and learn all about CECA products. At the end, you'll have a mini quiz, you get a certificate, and I'm quite there, they're trying to get the certificates from that to go for continuing education credits. And I'll just end with, that is something you can do at your own pace. You can start a tutorial, leave it, and come back. And as I said, it's very hard for me. I say I just busted 5 minutes, so I'll turn it back over to Nate.
Thanks, Frank. Much appreciated.
If I can figure out how to turn it back over to Nate.
All right, I got it.
Okay, thanks.
Phil, I saw you were online. Do you want to introduce yourself briefly?
Turn my mute off here. Yeah, I'm Phil Martinson. I'm in Spokane and excited to work with CBEC. I think CBEC's kind of the leader in the different associations, the local associations, and I'm very impressed with all your educational that you have available. And I'm excited for the people in Eastern Washington, Northern Idaho to get involved.
Great, thanks, Phil. Now I'd like to present Jeff Kerr with Engineered Assemblies, who is presenting on the topic of the 5 most common mistakes in the facade industry. He is a senior technical advisor with Engineered Assemblies and has more than 20 years of technical sales experience. We're excited to have him in from, is it Ontario here, Jeff? Take advantage of a little bit of these virtual means to bring in a wide range of speakers. Jeff, please feel free to take it away.
Thank you very much, Nathan, and thank you for CBEC for inviting me to speak. And I say Amanda and yourself, Nathan, I guess for reaching out to me and collaborating to make this happen. So with that in mind, I'll grab the screen and we'll start moving into tonight's presentation. I say
one thing I should mention real quick is that we like to use the question and answer form for taking questions. So all of our participants can type questions into that, and that'll give us a chance to answer them live. Either we can insert them kind of along the way, or we can get to them all at the end.
Okay. Very good. And if I can ask for your assistance, if you can monitor that, and yep. I try to make a point of checking in, but I get talking. And so with that in mind, with your assistance, we'll get through this. And I invite people, of course, to ask any and every question that they have. 5 most common mistakes made in the facade industry. I guess one of the things we could do a little introduction on is engineered assemblies. Who are we, and what do we do in the facade industry, and what do we know about the facade industry? So EA, Engineered Assemblies, is one of Canada's most trusted facade companies. We're nationwide, so from the East Coast to the West Coast, we have representation through the whole country, and we do assist in some projects down through the United States as well, because we have some products that lend themselves well to your markets. And we've developed a few good systems of our own, which are very applicable. We're about, I can say moving on about 13 years of age now. Our war cry for a long time, and still is today, is uniting the house of design with the field of construction. So our fearless leader, John Kubicek, when he was creating Engineered Assemblies, he wanted to make a point of having a company that not only represented a variety of architectural products for facades, which is ultimately what we do, but he said, one thing that's going to be different about us is that we're going to be able to speak architect speak, engineer speak, and contractor speak, unite the house of design with the field of construction, and maybe most specifically, understand how materials get on buildings. Not just materials and their particular, understanding their data sheets and their performance criteria and all that kind of stuff, but actually understand detailing and how materials get onto buildings, because that's what really puts the rubber to the road. So that is something we consider ourselves modestly to embrace a certain amount of expertise within that realm, and but maybe more than anything, we're built on a premise of do the right thing. Do the right thing for the environment, do the right thing for people, do the right thing for construction in the interest of bettering the built environment. So the last point being grow the whole pie mindset. That's what allows me to put on presentations like this, because I can speak, I don't have to be promoting engineered assemblies so much as talking about various subjects. And what I mean by that is we've always had the attitude of engineered assemblies is not going to take over the facade industry in Canada from a material supply standpoint. Actually, no one body is going to do it. We're going to have to share it. We've all got some good quality products, and if we all work together growing the whole pie, each of our pieces is going to get better. And through that selfless attitude, we can divert more energy towards understanding our craft better and making things better for, as I say, everybody involved. So that, I think, may give you an idea of who Engineered Assemblies is. And I invite you to visit our website, engineeredassemblies.com, and get in touch with us, ask us questions about what we do, and because we're more than happy to share information. This is a good slide to start with. Sort of speaks of where we are right now and where we're going. So this is well, it's from the Greek philosopher Heraclitus, but it's part of an iron bridge in Toronto that goes over a river. This river I step in is not the river I stand in, and it suggests that change is a constant. It's probably the only constant that we have, and I think we're experiencing that now. That's definitely a wave right now. We're in a transitional point of embracing some new technology with respect to facades and materials, and we're moving forward. So there's definitely an evolution that's happening there, but also we're in a change to a certain degree environmentally. We're experiencing some different weather that we've probably not been familiar with in this particular fashion. With respect to more occurrences of extreme weather bundled together, this is a challenging time for facades, for building envelopes, because as I like to suggest, building envelopes, building facades in particular, are the infantry. They're the front lines. So when there's radical changes, increases in wind velocity or precipitation, jumps up and over the freeze-thaw line, back and forth, the facades can bear a lot of that brunt, and they're protecting the building to a great degree, especially when we consider outboard insulated systems are becoming more and more prevalent. So they have a big responsibility to do, and it's up to us to make sure that these things are engineered, designed, and installed correctly. So we've got some weight on our shoulders here, and ultimately we're going to have to do it with intelligence, because we're not building walls or facades or envelopes out of 1 yard thick natural stone or 2 feet thick natural stone anymore, because we're in this point of transitioning into lighter weight systems, less mass, less embodied energy. We have to compensate with better engineering, better design. And these systems we're moving to have incredible potential. They're already delivering, but they could even deliver more. So just like the cars of old, we've got newer vehicles which weigh less, and we've compensated with the brawn of yesteryear. We've compensated with things like crumple zones and airbags. We've made the vehicles resilient through better engineering, better design. And that's no different than facade systems, because ultimately the forces that are pushing and pulling against facade systems, we're not going to beat them with muscle. We don't beat Mother Nature that way. We have to be involved in a dance of give and take, push and pull. And we can do that with clever engineering and good design and good installation, and come up with a system that can flex when it needs to flex, and not break in the face of say environmental adversity, what have you. So I think this is something to take into consideration. It's important to note that, as I suggested, the environment right now is a substantial dictator. We're designing our facades around materials that are trying to be sensitive to the environment. We also have to be respectful of the environment from a climatic standpoint. So we're using materials with less embodied energy. Now, that's a 2-part component. There's initial and recurring embodied energy. Initial, of course, being the energy that's involved in the fabrication of a material and locating it to site. But then recurring embodied energy is the energy it takes to manage a material, maintain it, and potentially replace it if it doesn't meet expectations in terms of lifespan, longevity. Well, so that's a challenge, because in many respects, when we're building something lightweight and low mass, the immediate thought is that it's not going to be tough enough, but that's not actually the case. It doesn't have to be that way. We're also having to build with higher thermal performance. And as we've suggested in the last few minutes, climate change is challenging our construction materials like never before. So, but this isn't, as I say, this is not a restriction. These are only some factors that we have to consider to help us navigate through, say, our direction that we're heading in to build good facades for the future. So within this low embodied energy, we've got the potential of using materials like fiber reinforced cement, high density systems, phenolics, ceramics, porcelains, certain metals, but also we have to consider the systems that are supporting those, because there's a synergy there. They work hand in hand. So the substructure that's supporting them, that may be just as important as the materials that are on the face, the skin. So that all has to be considered, and how those are detailed and installed is critical. So as I say, not limiting, we can use some of these materials to embrace the contemporary design ideals that we have today. And there can be a use of these materials, of course, to address historical content, but do the cutting edge things, the gritty and daring architecture and construction that we want to do to address, as say, our times, our contemporary times. And so we've got materials. We've got materials that are designed to take us into the new era that we've been in for a bit and are moving further into. But it can't be done carelessly. So enter today's subject, 5 most common mistakes. These are not all of the mistakes, but they're the common ones. So we're going to talk about this, and it's not meant to be a finger pointing or a negative a presentation, but rather it's meant to highlight some of the realities that we need to address, some of the things that we can't ignore. And these are equally from an installation standpoint as they are from a design standpoint, an engineering standpoint. So we're going to look at ventilation. We're going to look at coefficient of expansion, contraction, substructure, design emissions, shortcomings. We're going to look at deflection limits and shop drawings as part of lightweight facade systems. And I guess most specifically, and I'll elaborate on this, we're looking at Rainscreen systems specifically for all intents and purposes. Now, a lot of this material is covered in the Engineered Assemblies design guide in terms of proper direction detailing. This is a design guide which is available for free download off our website. The beautiful thing about this design guide, besides it being an incredibly complete, comprehensive guide to detailing outboard insulated, thermally broken Rainscreen systems, is this is not applicable to merely Engineered Assemblies materials. This is applicable to so many materials in the market. Many of our competitors will refer to our guide. It's a guide which, as I say, addresses the science of outboard insulated, thermally broken Rainscreen systems. Materials, myriad of materials can fit within this. So I invite you to download a copy of this. You can always request a hard copy from us. I prefer those. They're easy to flip through and carry around. But with that in mind, I'll be referring to it a couple of times within this presentation. And so I invite you to get yourself a copy. So what type of Rainscreen facade system are we really talking about here in this presentation? Because I know when people mention the word Rainscreen, there's probably as many definitions for Rainscreen as there are for the term free range chicken. So a lot of different designs of it. The version that I will be referring to in this presentation is something we call an RVRS System 2. And that's a title that Engineered Assemblies coined. And RVRS stands for Rear Ventilated Rainscreen. And System 2 is the particular design of it and all the particular idiosyncrasies that go into how it works. But this is based on, down at the bottom of the screen here, DIN standard 18516. This is based on a German standard called ventilated facade. This is not new. This is nothing that Engineered Assemblies invented or created. We simply took a well thought out system and then applied some, we'll say, Northern North America sensitive engineering to it to address more of the cold temperatures and the swings in temperatures that we experience here. So what have we got here in this system? Okay, well, we've got our skin on the outside, which is featured in red. So that could be, as I say, fiber cement, a phenolic, it could be an aluminum panel, anything along those lines. And then directly behind that, supporting it, we've got a vertical substructure, okay? That vertical substructure is going to be an 18 gauge galvanized girt. There is an EPDM membrane that sits between the panel and the girt. But the most important thing here is that that girt is vertical. That girt is vertical. It is the last frontier of substructure that supports the panel, and it creates an unobstructed vertical plenum, a chimney effect, okay? So this is something I'm going to talk a little bit more about in the next couple of slides, but ultimately that's the most important thing about this slide moving into this chapter is unobstructed vertical plenum. So we don't have any horizontal members directly behind the panel, okay? Behind that vertical girt, we've got a weather membrane. This is not an AV barrier. This is a high perm rate breathable membrane that features a capacity to keep the insulation behind it dry from precipitation that may come through the open joint system of a panel. So it's going to defer that precipitation. Also, it may help to protect the insulation if the insulation is not UV stable, because that membrane is UV stable, okay? So it's going to keep the insulation plane dry. It's going to protect the insulation from from UV damage. It's also a black membrane. So when you, it's something that we get from SRP. It's called air out shield. And what's fantastic about it is that when you look through the open joint system of a panel layout, you don't see a name brand upside down or anything like that. You just see black. And that makes sense because the, as I say, the open joint system sort of fades into shadow, but we aren't going to be staring at insulation. Okay, and then behind that, of course, we've got our insulation plane, which sits, as you can see, we've got a thermally broken substructure in there. Okay, so thermally broken substructure, outboard insulated. We've got a membrane to protect the insulation, something to defer direct precipitation to flow downwards. But we've got a vertical unobstructed plenum, and then we've got a panel in front of that. This is an RVRS system too, okay? This is what we consider a very good high performance, relevant Rainscreen system for today. But ventilation. I don't know if you can have too much ventilation within a facade system, within an envelope on a facade. Because certainly, as you probably experience in the Northwest, precipitation, moisture can be abundant, and you need to find a way to manage that. We get our share of moisture in the east, certainly in the east coast of Canada, and but wherever you are, there's going to be a necessity for ventilation because it's not just managing moisture. So we've got an uninterrupted vertical plenum. It's open at the bottom of, in this particular case, and these things vary per region from a code standpoint. We can go 6 stories in Ontario with an uninterrupted plenum, okay? In some regions, because that plenum could be treated as a fire chase, you'll need to have a through wall flashing. But for the sake of this particular slide, we were going 6 stories. It's open at the bottom, it's open at the top. Air comes in at the bottom, goes up, comes out the top and exhausts. We've got this continuous flow, okay? The beautiful thing about this is, as I say, if we've got some solar heat gain bearing down on the panel, that heat's going to go inboard, that air is going to get hotter, it's going to move even quicker. So we're going to have this nice quick circulation, which is going to create a vacuum. And that vacuum is good because it's going to be pulling as it moves in circulation, it's going to be pulling on just about anything it can get its hands on. And in a lot of the cases, it's going to be pulling on vapor. Okay, so if there's any moisture within that envelope system, if there's any moisture trapped in that insulation, it can move through that high perm rate membrane that we talked about, and the vacuum can help pull it out. Okay, it's constantly working, always working. So this is an important component, and this must be addressed from a detail standpoint, designed correctly, and it has to be installed correctly. It can't be interrupted. There's a microclimate in this plenum, and this plenum, I should suggest, is 1 inch deep. I should have mentioned that earlier. I apologize. It's a 1 inch deep plenum. Okay, so the climate in this little plenum is not the climate on the outboard side of the panel. It's not the climate on the inboard side where the insulation is. It's its own separate little microclimate. Okay, and it does help to defer. If there's an abundant amount of solar heat gain coming down on the panel, it will exhaust some of that heat and relieve the panel of that strain, okay, from that heat energy. There are very few materials that benefit from excessive heat. And so it's going to help defer some of that and exhaust that heat. And then, as I say, apologize for the barking. Sorry, just a second here. So as I say, that active plenum is going to help relieve some of the strain from the heat on that panel. And of course, let's face it, on a hot August day with the heat coming down on a building, we don't need that heat working its way, trying to work its way through the insulation, challenging an environment within the building that we're trying to keep cool. Okay, so we want to, in that particular sense, we want to get as much of that heat out, and it will move out because hot air rises faster, of course. So you can transpose this into winter applications, etc., and just helping to create some balance in terms of the deltas of temperatures that occur, because it's when you've got differentials of, for example, temperatures on the inside and outside of a panel is when panels are also challenged to a certain degree, where surface tension can vary. Ventilation. Ventilation, a big component of DIN standard 18516, a big component of Engineered Assemblies RVRS System 2. Some common mistakes. Flashings get installed. Sometimes flashings get installed on a parapet by the roofing trade, which is not doing the facade. They're not sensitive to the detailing. In this particular application, this is a louver assembly for ventilation into a building, and or it could be a window. But we have to ensure that these flashings are set up in a way that this plenum can exhaust correctly, and perhaps on the bottom that it can be a proper intake for that ventilation. And all these details and dimensions are laid out in the Engineered Assemblies design guide on how much, how many, it's laid out in metrics, so how many millimeters of space is permitted or should be allowed for to have the proper ventilation. And it's all set up for a 1 inch plenum, a 1 inch cavity, okay, which is an adequate amount of ventilation for most materials. So when we talk about this thing being open at the bottom and the top, well, it is open at the bottom and the top for air, but we generally engage 50% perforated screens, and that eliminates friends from making a home within our plenum. Okay, so birds and bats are the primary concern. Most insects are not that interested in being in a plenum because of the active nature of the plenum. It's straight up, it's not good for mating. So wasps in particular and creatures like that that most people are not interested in, they're not interested in being in a plenum. There's the gusts of air that can move through a plenum are not conducive to their lifestyle. This is the kind of stuff that we're talking about. But when we look at installations where spray foam is engaged, et cetera, and in the application of the spray foam, they didn't respect the limits of the spray foam, and the spray foam ends up expanding through its installation and blocking off the plenum, then we have a problem. We don't get proper ventilation. It can affect the panel poorly in a negative manner. It can affect the ventilation and the breathability of the insulation cavity, and everything suffers because moisture is allowed to collect. So these are issues associated to ventilation. And we talked about, the benefits of ventilation and how it works for the integrity of the panel, the installation component, and of course, offering a balance in terms of temperature deltas and what have you. So there's a component that is necessary. There's a necessary amount of energy that should be employed to make sure that this is managed correctly. So chapter 2, dynamics of facades, how panels react with one another and their fastening system, hot and cold, expansion, contraction of materials. This is an important component. Oftentimes when we see failures of facade skin systems, which are either in the warping of panels, the tacoing of panels, or the cracking of panels, shearing of fasteners, it's because allowances for expansion contraction were not managed properly. So, and particularly when we're looking at lightweight rear ventilated Rainscreen systems, again, lightweight materials, low mass materials are typically more prone to expansion contraction than high weight, high mass materials. So we have to address that. It doesn't make them more difficult. As I say, we have the intelligence to work around this kind of stuff, and we have been doing it for a while now. We just need to make sure that we're paying attention to these types of realities. So something, for example, that we employ is when panels, let's take, for example, reinforced, high density fiber cement. You're going to have a face fasten system, for example. You're going to use a rivet system to fasten those panels. Well, all the holes on a panel for all the fasteners need to be over drilled. Okay, there needs to be float. So we'll refer to them as stop and go points. There's going to be 1 or 2 fasteners on a given panel. Let's say that panel is 4 by 6 feet. There's going to be 1 or 2 points on that panel where the fasteners are not going to have float. So if we look down here on this slide, down here in the bottom right corner, we can see there's a fastener with a shank. Okay, we can see just above it, that shank, there's a space for the over drill for the larger holes, but down at the bottom, we're going to have a shim employed that's going to take up that space. That space is, that scenario right there is now what we call a fixed point. So that panel is supported there from that point. It's located from that point, and it expands and contracts from that point. But all the other fasteners on the panel, of course, are going to have a few millimeters of float between the fastener and the holes that are drilled. Okay, our fixed points hold the panel supported in place. They can handle the shear, no two ways about it. but the rest of the fasteners are going to have float. And this applies itself to phenolic panels, to aluminum composite systems, et cetera, which everything expands and contracts. There needs to be fixed and floating points. So oftentimes, in fact, I'd probably say 9 times out of 10, whenever I get called to a site because there's an issue with a panel that is not performing properly, either because it's cracked or warping, it's almost always because fixed and floating points were not addressed. They were either ignored or not part of shop drawings or some component of a series of directives. It's also important to consider that it's not just the panels that are expanding and contracting. It's not just the skin. It's also the substructure behind it. The substructure is going to move. The panels are going to move. Buildings are alive. Buildings are dynamic. Things are moving. We need to account for that. And it's a mistake to not account for that. So in the spirit of this presentation, 5 most common mistakes, yes, we need to account for expansion, contraction, and movement, and especially with the swings of temperature that we've seen. And I know that in the Northwest, you certainly get some crazy swings of temperature, just as we do in the East, and potentially over and above the freeze-thaw line, which is very detrimental to a lot of materials. We've seen some crazy swings here. And it's systems like this which help save skins and what have you. Now, we had a project actually in Whitehorse up in the Yukon, is up there near Alaska, where we had a terrible failure of within a project, and that was specifically because every single point of the panel system was created as a fixed point, and they get a lot of earthquakes up there. They can be very small, but I think the number was something like 265 earthquakes per year. It's almost one every, well, it's 2/3 of your days. There's a small earthquake to some degree. Well, amazingly enough, when a lot of this technology is employed, it can manage a lot of low tremor, low Richter scale earthquakes simply in the float that's put in within the systems, within the substructures, within the panels. So that's a bit of an extreme example, but certainly for the rest of us, and I know in the Northwest, there's a sensitivity there to tremors and what have you. So something to consider. But as I was suggesting before, a typical panel layout, we'd have a couple of fixed points and then all the rest would be floaters. And as you can see directly behind the panel, we've got our vertical bars for our unobstructed vertical plenum. So this is an example looking at a panel system where a fastener, a rivet, is not centered within the float, within the hole, the overdrill. So if our rivet shank, let's say, is 3/16 and our hole drilled is 3/8, we've got a decent amount of float there, but it doesn't serve us if the fastener is hugging one side of the hole, and that creates just another fixed point. That's all that is, and that just equates to stress. So we've got specific tools, and there's tools that are common in the industry, centering tools to make sure that fasteners go in. Now, as I say, this presentation does deal with some fairly technical ideas that may be in some respects minutia, but this is the difference between facade systems lasting their 50 years, their 60 years expected lifespan, or lasting 3 years. What we want to do is make sure that systems are specified correctly, standards of performance are clearly outlined, and that warranty requirements are met. This is very, very important. I mean, a building facade needs to be done at an execution level that serves all the materials in question as best as possible. And sometimes this extends even beyond manufacturers' simple instructions. And we need to go into some more advanced systems, particularly when some of these materials are coming from Europe, which in a lot of cases, a lot of parts of Europe do not enjoy the climatic conditions that we experience here in North America. So this is all to say, though, that this doesn't limit us. These aren't limiting factors. These are just factors that need to be considered and say they get practice on a daily basis to ensure that these buildings can go up properly, such as the building on the screen right now. A pretty sophisticated layout of panels. This is an opera house in Austria. This is a very small corner of the opera house. It's quite a large structure, and it has quite a sophisticated panel layout. And everything about this here is enjoying the engineering of fixed and floating points. So with that in mind, say this is the second component. Say we've got ventilation and then coefficient of expansion contraction of specific panels that needs to be embraced. So why don't we take a moment here and see if there's any questions that need to be addressed. Nathan?
We did not get any questions in the question and answer.
Okay.
But if anybody wants to jump in, please do. I had a question though.
Okay, sure.
In your Rainscreen diagram, you had I think it was 1.5 centimeters for your inlet and your outlet, and 25 or 2.5 for your vertical cavity. Is that something you've just kind of balanced? Like, is there research behind that, or what generates those differences?
There is research behind that. I mean, to a large degree, we do follow some of the German engineering behind the DIN standard, but also we leaned on engineering that, say, Engineered Assemblies sought out to find out just what was required, because ultimately, the DIN standard actually calls for 19 millimeters, which is probably just shy of 3/4 of an inch for an active plenum. But because we employ what we call a bird and bat screen, with that 50% perforated screen, we limit to a certain degree that plenum. So we found in our calculations, we had to open it up to 25 millimeters, which makes it an inch. So the intake and out and exhaust dimensions that you just cited, those were the ones that we relied on, like as from the standard, and then we blew the cavity open by an extra, not I guess 3/16 of an inch for all intents and purposes, or 1/4 inch, because of the employment of the bird and bug screen. Yeah. And it was to keep the flow, and all this is to be, all this is, we, based on the science that we have and that we've referred to for Rainscreen systems, pressure equalization is not something that can be attained for all intents and purposes over the course of a whole building. Not an equal amount of, well, not an equalization, but rather a pressure normalization. We can enjoy that. I mean, where winds whip around the corners of a building, obviously you have pressure differentials, etc. So things are changing. Buildings are dynamic, Rainscreens are dynamic, but that the calculations to give us those dimensions were something that a lot of work went into. We estimate we probably put about $300,000 of engineering into that design guide over the years. It's so a lot of engineering went into figuring out a lot of this type of information. There was a question here though, is it the panel manufacturer who determines where fixed or floating points are located and how many? We do rely on the manufacturers to guide us where the fixed and floating points. Usually the fixed points are always as close to the center of the panel as possible. We don't ever want a fixed point on the outside perimeter of the fasteners. So they're always tend to be located towards the center of the panel. And then the perimeter is always the floating points. And how many? Interestingly enough, with some of the high density fiber cement materials we're dealing with, they call for 2 fixed points where the phenolic manufacturers only call for 1. Now, that isn't really unique to the material. It just seems that when you're dealing with a particular panel, and let's say it was a large panel that was oriented horizontally, they figure, the fiber cement people figure, with 2 fixed points, they could manage any tipping of the panel that could occur over time. Whereas we find like the compression of the fasteners against the panel, while it's not choking the panel, there's enough compression to ensure that panels actually don't tip to any certain degree. But in order to embrace manufacturer's warranty requirements, we honor the 2 fixed points within the fiber cement world. And, but we know that 1 fixed point from a shear standpoint of the fastener to support the weight of the panel, 1 stainless steel rivet, certainly the ones that we use, is sufficient. So I hope that answers the question.
Where it's 2 points, it's always the 2 like adjacent.
Yes, they're always side by side. And then there's some rules in terms of, as say, if they're employed vertically, they're not to be on the same vertical channel, though. So, and this is all of this criteria is laid out within our design guide. It's very, very clear. So we have a bunch of rules, and I think I've got some slides that may even show that. So what I'll do is we'll keep hopping along here, and then yeah, and as I say, as questions arise, let's knock them out of the park. Yeah.
Great. Thanks for the question,
Yeah.
Ken.
Okay, so substructure design, omissions and design omissions and installation. So again, this is talking about the dynamics of buildings and substructure and structure, superstructure. Where we're looking at vertical expansion contraction of substructure, we know that, well, one, if we're employing some vertical members behind the panel to support the panel, and let's say for the sake of this presentation, we're talking about omega channels, which in some terms people refer to as hat bars. If we've got those and we're dealing on a multiple story building, then we're going to have a number of those hat bars moving up the building supporting the panels. Now, there are rules about this. Okay, first of all, whenever you have 2 sequential bars, they're to be separated. In this case, we say 3 millimeters. They could actually be further than that. Because there's expansion contraction of those members and there's movement, we need to separate them. We can't have them butting into each other. Okay, that's an important component. And when we're looking at this, vertical hat bars have to stop and start at traditional points of deflection. So let's say for this example, we're looking at steel stud and concrete slab construction. With that, we're going to have a natural deflection point at the concrete slab. Okay, so we reasonably. We cannot have a substructure, a lightweight substructure for that matter, crossing over that point of deflection. It has to stop and start there, okay? Because there's going to be movement. And if it's going to stop and start, we have to have a reasonable gap. And we also have another rule. We cannot have a panel, no matter what material it is, jumping over the gap of a substructure and fastening to two sequential members, okay? Because if those members either push or pull, push together or pull apart, what's it going to do to the panel? It's going to try to push and pull or tear the panel apart, okay? So we've got these extra systems in place. We've got the fixed and floating points of the fasteners. We ensure that at traditional points of deflection in a building, we stop and start our substructure. If we're looking at concrete slab, steel stud construction, it's reasonable to assume that when people are doing takeoffs and putting material together to erect a substructure, all their vertical hat bars or vertical mega channels for the substructure are going to be the size of the floor to floor or slab to slab dimension. It's very simple. They get ordered custom length, but I shouldn't even use the word custom because custom seems to denote a higher price. The fact of the matter is that they're always cut to the size people need them, just like studs are. And they're ordered to suit the building. Okay, so those members go from slab to slab. And when panel layout is being done, and this is being done from a design standpoint, again, at the architect's end, they have to ensure that there's going to be a stop and start point of panels at traditional points of deflection because we know that our substructure is going to stop and start there as well. Okay, so what we can't have, this is a mistake, what we can't have is we cannot have, let's say, 25-foot long hat bars extending up a building going way past our traditional deflection points, our slabs. And we certainly can't have them, as we can see in the left here, where they simply stitched the hat bars together. They put one over top of the other, fired some fasteners through them. What they're creating here is a lightweight, light gauge net around the building, expected to contain the movement that this superstructure is going to experience. It's ridiculous. It's going to pull this net apart. And when this light gauge net starts to get pulled in various directions, what's going to happen? Our panel system is going to suffer. It's going to crack. It's going to taco, what have you. So these are mistakes. These are mistakes that happen from a design standpoint at the shop drawing stage, or they happen at an installation stage on site where someone makes a decision to just ignore that traditional point of deflection. But also from a design standpoint at the design end, we need to ensure that when we're looking at a building, every time we get to a floor, there's going to have to be a seam, a demarcation point within the panel layout, okay? Now, that line that, as I say, where panels stop and start, that doesn't have to be a straight line across the face of a building, because panels can cantilever over top of these stop and start points of substructure. They just can't fasten to the following member of substructure, but they can cantilever. So we could have panels moving up and down, over, top, below this particular point, this line. And with that, we can have a perfectly agreeable design. And I think you'll notice in this particular building, which is a very well-known building in Toronto. It's a very successful, say, community building. It's assisted living in Toronto called 60 Richmond, Toronto Community Housing. And this building enjoys a decent degree of, say, tasteful design. And no one, I guarantee you, no one is staring at it going, oh, geez, would you look at the god-awful seam in the panels at the floor-to-floor points. It doesn't get picked up. And there's say, an enjoyable degree of design in this building, and it works very well from a structural standpoint. It works very well. So again, crossing over traditional points of deflection with panels or with substructure, big no-no. And this is a design element, and this is an installation element. So if we're going to have these lightweight, low mass systems working, we need to respect this. We need to respect the expansion contraction they have. We need to respect the ventilation they require, and we need to respect the live nature of the buildings that we sometimes find ourselves designing. Now, of course, when we get into timber construction, slightly different animal there, because as I say, there's in this particular example, there's a lot less expansion contraction that'll happen in the mass timber design of a building, say in this particular direction. But that's a subject probably for another presentation.
Jeff, we did get one more of a comment.
Go.
Said the IBC only allows 10 feet of vertical plenum. So you had talked about the possibility of needing fire stopping and things like that.
Yeah.
Does that change the approach?
We would probably just need to have a through wall flashing, or it wouldn't necessarily need to be through wall. It really just needs to, the flashing would just need to cut the plenum off. Okay, but we would still have our intake and our exhaust, even though we've got a flashing going through. So if 10 feet is the extent of a 1-inch plenum, then it's very conservative, but if that's the case, then you would have a flashing go through and stop and start that plenum. Now, amazingly enough, I was in conversation with an American outfit who was talking about an intumescent membrane, actually, that could be used. We're looking at this as well, an intumescent membrane. So what would happen is that in the case of a fire, the membrane, of course, would act like an intumescent material would, and it would swell and block off the plenum. So as soon as fire reached the membrane, it would cut off the plenum. And so that circulation wouldn't happen. So that's something I would look into. I cannot, the name escapes me right now of the particular material, but it was a US outfit that had this type of intumescent membrane. That's something to consider, especially when you're looking at something as low as in depth as an inch. But otherwise, our response in Ontario, Canada, where we're restricted to 18 meters, or about 6 stories, is we have a through wall flashing. That's what generally occurs. Does that answer people's questions?
I believe so.
Okay. Okay, so control joints. Actually, I think I'm going to make an adjustment. I think my screen just went a little dim. Is that, or is my screen well enough lit for people, or is it a little on the dim side?
I think it looks okay here.
It does? Okay, okay. I won't make any adjustments then. What do we got? Comment, looks okay. All right. All right. Well, with that in mind, so ultimately, and last point about this, control joints. This is all part and parcel of the Engineered Assemblies design guide. We address control joints within buildings, how to detail them accordingly to use this type of a system, rear ventilated Rainscreen with thermally broken substructures, etc. I can't say enough about the design guide. We've put a lot of resources into it, a lot of thought and engineering. So it's a simple enough guide, but it has it's comprehensive at the same time, has a lot of information, and we're always open to questions and challenges to address, you know, unique circumstances. So certainly get in touch with us. So moving along to our presentation here, as we're coming up on the hour, chapter 4, poor deflection limit of substructure. This is something that this is a mistake that gets made where it can be the say the cost of some facade systems. And with that in mind, we call on L over 300 for maximum deflection value for substructures. This is a simple enough deflection value to obtain. It's very easily obtained with 18 gauge substructure components, and 18 gauge offers great pullout. So the cost differential between 20 and 18 is nominal. So it's and this ensures that we're not getting a ridiculous amount of deflection, or rather, maybe not ridiculous, but a deflection amount that panels, you know, can or cannot manage. Okay, because a lot of metal systems, for example, might be able to manage a much higher amount of deflection, but when you get into high density fiber cement systems or glass fiber reinforced concretes and also phenolics, they want things that are stable. They want things to be stable. Rather, they want substructures, especially in through the plane flexibility. We want that to be as stable as possible. Part of how we achieve that is by using, as I referred to earlier, hat bars or omega channels. Z bars do not enjoy the same strength and the same potential for deflection limits as hat bars do. So certainly recommend that people go the hat bar route, the omega channel route, and people are able to create them in a variety of depths and of face widths to accommodate a variety of panels. I think you'll find that when you get into our design guide, you'll see quite an array of different hat bars that get employed for different conditions, external corners, interior corners, and the like. So this is something that we consider very important. It's a small factor, but a deflection limit of L over 300 lends itself significantly to the success of say lightweight, low mass, rear ventilated Rainscreen facade systems. Now, this all of what we've been speaking about here, it's amazing how we need to talk about this stuff nowadays, because in some respects, people have a lot of balls in the air from a design standpoint, or from an installation standpoint. We either don't have the knowledge or the care that we need to have to do this. There was a time when architects could design something and make good on drawings. And that was enough because everybody understood what was trying to be achieved, and everybody stood the right way to do things, the proper way, the quality way to do things. So when we talk about due diligence, as far as a construction contract is concerned, is placing an obligation on the contractor to complete the works with care and requisite effort. And when we look at that, requisite, I mean, that's a thing that is necessary for the achievement of a specific end, and that specific end is quality construction. So this whole presentation and the article I wrote for Constructing Canada back in June 2020, this was all sort of arriving out of a discussion around these terms here, that if we understand the materials that we're working with properly, and that understanding is out there, it's science, and we have a handle on it, and proper training and for installation and proper execution of installation. We have worked with these materials successfully. We can continue to do it, but we have to keep our foot on the gas about this. So, and if we don't do that, failure to provide, this type of quality is going to result in failures, and we can't permit that because it's so easily avoided. So in the interest of having our facades for the future to address the needs of our, say, built environment, we need to make sure that that people are say, not making mistakes, such as the mistakes we're talking about today. So to sort of wrap up this presentation, shop drawings is the last chapter. Shop drawings is a good topic, because I think everyone here has probably seen good shop drawings and really poor shop drawings. And good shop drawings are really just good instructions. And when one has a really good set of shop drawings, then anybody who understands their trade can walk in, open up those shop drawings, and have a clear understanding of what is required and what goes where. So that is a very basic, fundamental explanation, understanding of the necessity for good shop drawings. And when I have been called to site to inspect a failure, I've sometimes been amazed at the poor shop drawings, and it doesn't amaze me at all as to why these failures have occurred, because the shop drawings are so poor. And good shop drawing should start with a system drawing. And the system drawing should be a full-page explanation of all the fundamentals of the system that is being employed, in this case, a facade. Okay, all the fundamentals. And there should be good liner notes explaining every single item that is going to be employed within this system. So no rock should be left unturned, okay? Good principles on, for example, the whole idea of having gaps between sequential vertical hat bars and not having panels jumping over top. All these principles are laid out within the system drawing. And maybe if the system is sophisticated enough, it requires 2 pages of system drawings, but it can usually be done in 1. And this is what I call a good set of shop drawings is the truth. So people can look at this and read through it and understand. And if they have questions, they can call someone like ourselves or whoever is behind the system, and they can walk them through it so everybody can understand. And in a good set of shop drawings, there'll be pages that'll show every single elevation of the building. And on every single elevation, it'll show the layout of every single panel, every single module size, and it'll also show where every item of the substructure is being placed. That goes for the horizontal members within the installation plane. That goes for the vertical members, which sit directly behind the panel. All of those members of the structure, substructure, and the panel layout will be clearly spelled out in those elevation pages. Okay. Now, I'm not going to mince words. Good shop drawings are expensive. They cost money, but they're a fraction of the dollar amount of a complete facade installation, material and labor. And they can be the difference between a system failing or succeeding. And when facades fail, and facade systems fail, they often fail after the labor warranty has diminished. Okay, they usually fail 2-3 years down the road, or maybe 5-6 years down the road in the face of a 10-year facade warranty or 15-year facade warranty. So the cost of good shop drawings is completely legitimized. Okay, and it should be a necessity to have excellent shop drawings. It's like driving. There's no room for average drivers on our roads anymore with too many people. Everybody needs to be a great driver, and that's a personal thing of mine. But we need to have great shop drawings on every project. Shop drawings need to be great. It also helps us down the road understand when something needs to be amended. We can get our hands on the shop drawings and understand completely how the system went together and why. Okay, so every single detail of every condition, very unique condition and non-unique condition of a building will be outlined as well in these shops. So we're going to have a system drawing to explain what's going on here, what's going to go on. We're going to have elevations outlining the placement of panels and the substructure members. And then we're going to have details which are going to show specifically how every condition on a building is addressed vis-a-vis the facade. So with that in mind, we'll look at the 7 factors for future ready facades. I'm just going to take a moment in our last few minutes here, and I think I'm running low on power, so I'm just going to plug in my laptop. So I'll leave you on this slide. I'll be back in a sec.
We will be wrapping up shortly, but if anybody has questions, please feel free to ask them, and hopefully we'll have time to address everybody's questions.
Okay, I'm back and we have full power. Okay, I'll whip through the rest of this stuff here quickly so that we do have time to address questions if they come up. So the 7 factors for future ready facades, we discussed a few of them here. Coefficient movement of individual facade panels, panel joint size and fastener location, an unobstructed rear ventilation for the panel and for the rest of the envelope, expansion gaps in vertical horizontal framing members to allow for deflection and movement of substructure and building structure, deflection strength, adjustability for structure misalignment. So we need an adjustability component because in most cases our buildings are not built perfectly straight here in North America. So we need to allow for that. And we need to allow the potential for post-disaster design requirement. So those are 7 factors. This is something that we address in the beginning of our design guide. And we address these components within the rest of the guide in the following pages. Engineered Assemblies is divided a certified series. I don't know if we're going to have time tonight to go into this. This is just it's a unique certification series that we're offering. It's being offered right now in Canada, so I don't know how it lends itself to the US yet. It could lend itself very well, I think, but it's essentially a pathway to compliance to make sure that things are met properly vis-a-vis manufacturers' warranties in terms of installation of materials, and that facade systems are installed correctly. But let's take a moment now and just revisit what we've talked about tonight here. The 5 big points, the 5 mistakes and the 5 issues that need to be addressed, that being, ventilation, coefficients of expansion and contraction, proper substructure design, and then let's say deflection limits, and the issue of shop drawings. These issues are critical to the success of lightweight facade systems in our rear ventilated Rainscreen application. And uniting the house of design with the field of construction definitely will help bridge a lot of this. The ability to say convey these items to all parties involved that are part of the success of a project. But we need to embrace the relationship between, as I say, environmental responsibility, design, construction, and the reality of extreme weather frequency. So with that in mind, I thank you for giving me the opportunity to speak to you tonight about these sensitive issues, and invite you to pick up a copy of our design guide and see how it lends itself to the architecture construction that you practice in your respective areas. I think it will be relevant. But with that, say, Nathan, are there any questions that I can address at this point?
I don't think we have any open questions right now. We can give folks a chance to hop in if they do have any additional questions.
Okay. Okay.
Not a very
Well-
lively crowd today. Must be all the warm weather we're having down here.
I guess so. I guess so. Well, I think I've sent a copy of the presentation to you. I did update a couple of things in it, and I could send you the updated slides, and you could share that with people, and they could take a look at it. And if there's questions that they have, as I say, certainly invite people to contact me, Jeff Kerr. I can be reached at jker@engineeredassemblies.com. And of course, we do have, Vancouver, Canada office. And I know that Darren, who looks after that part of the country, he's happy to go down into your neck of the woods and assist people if they need assistance with any of our systems. But yeah,
We did an anonymous question asking how to pronounce your city name.
Oh, city name, Toronto.
Is a Mississauga in the
Oh, Mississauga. Okay, so Mississauga. Okay, yeah, it's funny. I guess we think of Engineered Assemblies being in Toronto, but Mississauga is actually a suburb, and so yeah, so Mississauga. Yes, not a whole lot different than Mississippi, but yeah, in terms of similar usage of vowels and what have you.
Yeah.
But yeah, Mississauga, Ontario. Yeah, that's technically where the office is located, but we think of it as Toronto. Yes.
We've got a lot of thanks from Ken and Frank and Soph in the chat. But I'd like to
Great.
also extend our thanks for you coming to present. It's great to
Sure.
be able to bring some folks in from out of town, and
Sure.
we appreciate your time and effort.
You bet. You bet. Well, thanks for inviting me, and I hope some of this information was useful. And I'm happy to, let's say, I'm happy to address questions down the road if people need be. Okay.
All right,
So,
thanks, Jeff.
okay, you're very welcome. You take care.
You too. Bye.
Okay, bye-bye.